given by Takeshi Matsumoto, who, as you can see, is at the Department of Physics, Kyoto University. And he will be talking to us about insights from numerical simulations of the dissipative Euler flow. Takeshi, it's all yours.
Thank you. And yeah, thank you for giving me a chance to talk to you in this program. I'm very glad to talk to you about this ongoing project, which was not yet finished. So this is a joint work with Frisch and Szekelyhidi. So I'm going to talk about numerical simulations of mathematical construction of the weak solutions of Euler flow, which dissipates the energy. So in the title, I put insights, but I must confess the amount of insights in this talk is quite limited, so be prepared. Okay, so I will start with scaling of homogeneous isotropic turbulent flow. So when we look at the energy spectrum, and the Kolmogorov scaling tells us this energy spectrum goes like wave number to the 5/3, minus 5/3 in inertia range. So L is a large scale, eta is a Kolmogorov dissipation length scale. And in the physical space, we take the velocity increments over distance r, then the velocity increments scales with r to the 1/3. So this is the physical space interpretation of the Kolmogorov scaling. So here we have epsilon. So this epsilon is the energy dissipation rate. The energy dissipation rate epsilon can be defined with kinematic viscosity times this thing. So this is a Fourier coefficient of the velocity Fourier-Mohs velocity. And in the physical space, the dissipation rate can be calculated in this way. And also we have some important assumption telling that as the kinematic viscosity tends to 0, this energy dissipation rate stays some constant, which is independent of the kinematic viscosity. So this is a basic assumption. So we talked about the Kolmogorov scaling, and it has exponent 1/3. But now we have some evidence for this 1/3 is not the only exponent of the velocity increments. So namely, there's some model or some conjecture saying that the velocity increments has a general exponent, and this h is not limited to 1/3. So this is, for example, the Parisi-Frisch famous multifractal model for the turbulent flow. That was introduced to explain behavior of the higher order moments of the velocity increments. Okay, so in a conventional, the physical setting of the Navier-Stokes turbulent flow, we add the forcing at the large scale, and we realize statistical steady state. In this state, we have energy input rate that was pumped by a large scale forcing, and that is in a statistical sense equal to the dissipation rate. So we have some kind of non-equilibrium steady state, and so this energy dissipation rate is a small scale physical quantity, but the energy input rate is a large scale physical quantity. So in the middle, if the scale separation is big enough, in the middle we have an energy flux. So the energy flux is also equal to the energy input rate, and the energy flux is also equal to the energy dissipation rate. So this is a turbulent in a statistically steady state. So this energy flux, if here I denote by pi r, so this average, so in some sense we take the average, so this average energy flux becomes scale independent. So this is maybe the most important property of the Navier-Stokes turbulence. So that's a flux constancy of energy cascade. And this is perhaps the most important aspect of the turbulent flow. So how one can calculate this energy flux, the energy going across the scale R, that can be calculated with low pass filtering. So this U bar is a low pass filter of the velocity field here. So GR is a filtering function. It's a low pass filter function, and the scale smaller than R was basically eliminated. So this U bar, with this U bar, we can calculate the energy flux in this way. So this is what we call the residual stress tensor. And the scale, and this U bar, the energy of U bar satisfies this conservation law. So here is a viscous dissipation, and here is a flux. And this is the sweeping with the same kind of, the same grid scale. So we have this energy flux across the scale R that can be calculated with the low pass filter. And so we have some energy equality here. So here we set the kinematic viscosity to 0. Then this term vanishes. So on the right-hand side, we have minus times flux. And in some case, this flux becomes R independent. Yeah, let's assume such state can be realized with Isett case. And also this flux becomes positive and constant. And then, so this term can be interpreted as a dissipation for the grid scale velocity, or filtered, low pass filtered velocity. So this flux works as a dissipation. So this is rather important interpretation or observation for the low pass filtered function.
I have a question, please.
Yes.
You're assuming that the flux is an assumption that it has a sign, correct? No, on one hand, you want to prove there is dissipation. On the other hand, you assume that pi is positive.
Right. Yeah.
Which means it's an assumption that there is a cascade.
Yes. Yes.
Okay. Thanks.
Yes, but this is a rough physical argument, so I'm not really.
There's difference between physical argument based on physics and mathematical assumption. At this stage, it's an assumption.
Okay.
Correct? I'm asking.
Yes. Yeah, right, but okay, so yes, I assume the sign of the flux here.
Okay, so
yes,
you assume there is dissipation eventually. That's what. Thank you very much.
Yes.
Thanks.
Okay, so so now we come to the famous Onsager conjecture. In his paper 1949, so Onsager stated that turbulent dissipation could take place without viscosity. So this statement was not really attracted attention, but in the beginning of 90s, Eink and others formulate this statement in rigorous mathematics and theoretical physics. And then this conjecture was seriously considered by mathematicians and physicists, maybe mainly by mathematicians. So the Onsager conjecture can be divided into two parts. So the first part is the Euler equation can dissipate the energy if the velocity field satisfies this kind of the Helder continuity. So if exponent h is smaller than 1/3, then such solution can dissipate the energy. That's the solution of the Euler equation. On the other hand, so if the exponent is greater than 1/3, the energy cannot be dissipated. So this is the two parts of the Onsager conjecture. The second part was proven in 90s by Eink and Konstantin E and Titi. And the first part, the subcritical part, the smaller than the exponent smaller than 1/3, this part was recently proven by constructing solutions of the weak solution of the Euler equation, which actually dissipates the energy. So those mathematicians constructed such solutions in a mathematical manner and proved there are solutions of Euler equation which dissipate energy, satisfying this constraint. So this is also the resolution of the Onsager conjecture, or proof of the Onsager conjecture. So today I focus on the one construction by Buckmaster and co-workers published in 2019. So their solutions are defined in a periodic cube in 3 dimensions, and their solutions are non-stationary, and their solutions has a scaling property, namely the velocity increments scales like r to the power h. So h can be chosen as you wish between 0 and 1/3. So their solution is very much interesting. So in this talk, I will, so our work is, our final goal is to numerically simulate the mathematical constructions of Buckmaster et al. And applied the physical way of analyzing turbulent flow to those solutions, and then see what kind of characters we can get from these weak solutions of the Euler flow, which dissipates the energy. So today I will describe you their mathematical construction in physicist point of view, or more precisely as a viewpoint of a numerical experimentalist. And I will try to get some insight from the numerical simulations of their mathematical construction, and which can be useful for the physics of turbulence. So that's the outline of this talk. Okay, so this is one example of the numerical simulations of their constructions. And I show you here is the isosurface of the vorticity. So it looks like a very tangled vortex tubes. But for example, if you look at this surface, you can see some kind of stripes. And maybe here you can see some kind of regular pattern or some kind of periodic nature from this structure. And that's that tells us this is not the really random solution.
What is
but this is, hi, yes?
What does the subscript 3 refer to?
Yeah, I will come to that. I will come to that.
So regular that you'd think it was periodically repeated rather than in little bits independently simulated.
Sorry, I couldn't hear you well.
I said it looks so regular that it looks like a periodic repetition of
Exactly. Yes, I will. Yes, I will come to that.
I think he'll tell you. Give him that.
Okay.
It's free.
So just to remind what the weak solutions of the Euler equation is. So this is the classical incompressible Euler equation, and we consider the periodic boundary condition. So in order to define the weak solution, we need a test function. So this is basically the same as the filtering function, which I talked about some minutes later. So it is a smooth finite support in x and t. So we filter this velocity field with this test function in space and time. Then we can get u bar. So the weak solutions to the Euler equation is can be defined in this way. So all the differential operators are now acting on the test functions. So if U satisfies these equations, then U is called the weak solutions to the Euler equations. And there are some traditions to construct weak solutions of Euler flow before this Lellis and Lazarus and co-workers works. So that's the famous work by Schäfer and Schneiderman. Okay.
Can I make a comment here or ask
Yes.
a question?
Yes, sure.
Your definition is certainly correct and valid, but I would like to stress that
Yes.
this is in the absence of boundary, because otherwise you cannot take convolution, because otherwise how do you define it outside the domain, this convolution? It has to be either periodic or the whole space. Otherwise,
yes.
If you have boundaries, your construction kaput will not continue from here.
Yeah, that's good. Yeah, indeed. Thank you so much.
Because we take convolution with phi instead of taking phi at one point.
Your test function is a scalar or vector field?
It's a vector, but it doesn't matter. It can be scalar function.
Okay. So I'll give you a little bit more details of the constructed solutions. So so let's U be the time-dependent weak solutions of the Euler equations constructed by this work. So X this is in the unit periodic cube. So the time extends from 0 to capital T. So the capital T is some large time. We can arbitrarily fix it. And let's say the capital T is some large time. And this construction allows two inputs. So one is the total energy as a function of time. So we can prescribe this function E of T from 0 to capital T. So if we can choose some decreasing function, then it's a dissipative solution. And if it's oscillating energy, then it's not. Yeah, it involves some flow with increasing the energy. So the second input we can prescribe is the exponent, the scaling exponent. So we can prescribe the exponent h from 0 to 1/3 and arbitrarily smaller than 1/3. So we can prescribe two things in the construction. That is quite amazing thing. And they construct the solution in an iterative manner. So it's a space-time construction. So anyway, we need some initial velocity field, U0. It's given in a periodic cube and extending time from 0 to capital T. So from some previous velocity field, we add some perturbation field, what they called perturbations. And then we have the second iteration velocity fields. And in this construction, yeah, so if we continue this iteration, then sorry, this is Q. So as we iterate to the infinite times, then the U sub Q tends to some function, and that converges to the weak solutions of the Euler equation. And I need to say, yeah, okay, so then this UQ has some characteristic wave number, K sub Q, and this K sub Q is given by A to the B to the Q. So usually in the physics of turbulence, we we are accustomed to give characteristic wave number as a power of 2 or power of some number. But now the characteristic wave number with the iteration number grows not the geometric series, but super geometric series. This is quite discouraging when we like to do it in numerical way. So please remember, so this growth of the characteristic wave number. Okay, so a little bit more about the iteration. So they construct the solution in an iterative manner. And so this U sub Q actually satisfies the following equation, what they call the Euler-Reynolds system. So this is Euler equation plus some tensor. So this R sub Q is a 3×3 tensor, and which was named Reynolds stress by Buckmaster et al. And this tensor is actually error of UQ from the Euler equation, the weak Euler equations. And this error tends to 0 as we increase the iteration. Okay. So I told you their construction is space-time. Yeah, just to give some visualization, I draw some figure. So this is this axis is a time. So we construct the solution from 0 to capital T. So here we have U0 velocity field. So U0 exists from 0 to capital T. So the energy of U0, so let me call it E sub 0. E sub 0 is something like this. And we decided to have a prescribed energy, E of T, in this manner. So the energy of U0 should behaves like this. Then the next U1, according to the recipe of the Buckmaster et al. So it increases from E0, but smaller than the prescribed E of T. So U1 can be constructed from U0, and now the energy of U1 behaves something like this. And so this is a space-time construction. Okay, so something about the...
Takeshi, there's a question.
Yes.
In the previous slide,
Yes.
yes, okay, so you say that E is decreasing, so this plot, this kind of shows offsets, right? That's not a straight E axis. Because here you would think that it was increasing.
Yes, yeah, yes, in some part we can have, yeah, so actually this
I'm sorry, I'm getting the T mixed up with the iteration.
Yeah.
Yeah, okay.
Sorry.
Sorry.
Yeah.
Okay. So anyway, so the energy E of T, we can choose whatever we like. There are some conditions of the infant soup, but between this infant soup, we can choose arbitrary function. Okay. So yeah.
Sorry, to go back to
Yes.
the question of Lorette, can you go back, please?
This one?
Yeah, so you put here the EDT is negative.
Yeah,
This is if it is negative, namely it is satisfies the conjecture. That's what you mean.
Yes.
If you choose it in that, okay.
Yes. Yeah. If
Thank
you
you,
choose in that
yeah,
in such a way that yes.
Yeah, but E of T can be arbitrary in the construction.
Exactly.
Okay, thank you. Wonderful.
Yes. So okay, so this is a classical Euler equations, and this is and also their constructions the iterative manner. So at the qth iteration, so we have velocity field U sub Q and pressure P sub Q from time 0 to capital T. So this U sub Q and P sub Q satisfies the Euler-Reynolds system. So this Reynolds stress is error from the Euler equation. Yeah, since this U sub Q is not the solution of the Euler equation, so there are some kind of error which is expressed in the form of tensor, 3×3 tensor. So we go from Q iteration to the Q plus 1. So we add some perturbation to the velocity and perturbation to the pressure. So what would happen? So Q plus 1, we have another Euler-Reynolds system. So we have new error, R sub Q plus 1. The relation between RQ plus 1 and RQ can be written in this manner. So this EQ plus 1 is this one, and just putting the substitute this q plus 1 by uq plus wq plus 1, then we can express E error at the q plus 1 iteration in this way. So their strategy, Buckmaster et al.'s strategy to choose perturbation W sub q plus 1 is to reduce the error. So basically, we like to have smaller error than the previous one. So how can we do this? So yeah, I'm giving you a very heuristic argument here. If you are interested, then I just ask you to go to their paper. So in the q plus 1 iteration, we have added some perturbation here. So the error can be expressed in this way. So we like to have the next error is smaller than the previous one. So yeah, let's assume this perturbation W sub q plus 1 is a stationary solution of the classical order equation. Then we can safely assume this term, and this term cancels. And furthermore, we can set the length, the typical length scale of the perturbation is much smaller than the typical length scale of U sub q. Then the cross term can be small. So from these two assumptions or the setting, then we can just have, so these three terms are canceled, and this term is smaller than this one. So what we get here is just two terms. So this E sub q can be written with Reynolds stress, and this part can be also written with a tensor product, divergence of some tensor product. So we like to have W sub q plus 1 to cancel the error. Then we can have the smaller error at the q plus 1 iteration.
Is this NQ?
Oh, sorry. Yeah, this is Q. I'm so sorry. So this.
No. You're doing wonderful job. Sorry, we are asking because we really learning. Thank you very much.
Sorry. Yeah.
So
it's a rather unconscious thing. So.
No, Matsumoto, you're doing superb job. Just basically, I'm asking just to clarify. Wonderful job. Thank you.
Yeah.
Question from Lorette also.
Thank you, Ro. If WQ plus 1 is a stationary solution of the classical Euler equation, then the terms that should cancel are, if I'm not mistaken, dt WQ plus 1, grad big Q, and then the WQ plus 1 dot grad WQ plus 1. With itself, no? Not the cross terms, am I not right? If it's a stationary solution of classical.
Oh yeah. Sorry. Yes, you are right. Yes, you are right. Yeah.
Oh, okay. But in that case, think below, why is it a cross term instead of, and why, I'm sorry, it is a cross, yeah, why isn't these not a cross term?
Okay, so maybe there's some typo, I'm sorry. And yeah, that's right. Yes, that's right.
There should be two of those cross terms.
Yes, two cross terms. But yeah, that's right. Yes. Maybe I made some typo or something like that. Yeah. Anyway, so can we proceed a little bit? So. Okay. So right. So the perturbation is added to make the error smaller. So the yeah, maybe some typo or some yeah, sorry about this. So anyway, so this the main part of the error is coming from this okay, yeah, this part, So we like to have these equations should be quite small, and right. So then, and also the energy at the Q+1 can be just written in this way, but here, so UQ and WQ+1, the cross term is much smaller than this one, for example. And to make this energy closer to the prescribed energy, so we can have some condition for the energy of the perturbation. So if we choose the energy of the perturbation in this manner, then the energy at the Q+1 is closer to the prescribed one than the previous energy. So we add some small margin, but it's a technical thing. So basically we have two.
Question, please.
Yes.
Yeah, I mean, once can you go backwards, please?
Yes.
Yeah, so in all this is nice and beautiful, but then you ignore the correction and the pressure, at least in your hand waving argument.
Right, yes, in this case.
Ignore
yes.
the pressure contribution.
Yes, right.
Okay, thanks.
Yes. So we have basically the two constraints for the perturbation. So from the first constraint, then they consider some special flow, capital W, as a function of some tensor and the function of space. So it doesn't depend on time. So this is stationary flow, and the tensor such satisfies the tensor product of the capital W, gives you 3×3 symmetric tensor. So if this kind of flow can be constructed, then we can make this thing. Yeah, we can satisfy the first requirement. So if we can have this kind of flow, then the perturbation WQ+1 can be given by using this some special flow, and this argument for the tensor is a bit complicated. So this is the energy requirement times identity tensor minus this R. This R is a tracer's tensor, and if you take the tensor product of this one, this W, then this minus R part makes this part 0, and this identity part gives you this constraint. So if we can have this some special flow, capital W, then we can, then we can make the proper perturbation to satisfy these two requirements. Okay, so the next thing is, we talked about the error, but we didn't specify how to calculate the error from U sub Q. So that can be done by so-called gluing. It is proposed by Isett. So how this gluing proceed is in the following manner. So we have U sub Q and the energy of something like this. So we take two instants which are regularly spaced, and this interval is determined by the magnitude of U sub n. So from this time, so let's take UN and at time tau n j. We solve the initial value problem. We solve the classical Euler equation, starting from this velocity field. So we consider the forward classical solutions of Euler from here, and from this time we solve the Euler equation, the classical Euler equation, timing backward. So we have a forward solution and backward solution. So then we grew these two solutions And then from the glue solution, we calculate the error, the tensor from the glue solution. That can be done in this way. So we solve the classical Euler equations, the compressible classical Euler solutions. So let me call the forward solution by UF, the backward solution by UB. So we glued these two classical solutions of the Euler, and this chi is basically it's a partition of unity. So we mix the forward solution and backward solution. And if we put these glued solutions to Euler equations, yeah, we just calculate these three terms, then the right-hand side can be written with this forward solution, the backward solution. So on the right-hand side, we have this kind of expression, and this is nothing but the divergence of the Reynolds stress tensor. So by using the forward solution and backward solution, we can have one expression for the error. So that's very interesting way to calculate the error. So having described how to calculate the error, now we describe some special flow, capital W. So some special flow satisfies this equations, the tensor product of the space integral of the tensor product so the integral gives you some constant 3×3 tensor. And how can we make this kind of flow? That can be done by what they call the so-called Mikado flow. There are 6 pairs of axisymmetric jets. So this is a visualization of the Mikado flow. One example of the Mikado flow. So here I showed you the vorticity isosurface of the Mikado flow. There are 6 pairs of jets. So one pair has the different direction of the jets. So there are other constraints for some special flow. So the space integral of the capital W is 0. The tensor products, as you know, satisfies these equations. And one example can be given in this way. So the section of this jet is a Gaussian profile, and this plus and minus means within the pair, the one jet going down and the other jet is going up. So this is plus and minus. This kappa m is the direction of the jets. So there are 6 directions. And if we calculate the tensor products of this one, we just, if the jets are thin enough, then we can have this kind of expression. And yeah, so this gives you some 3×3 symmetric tensor. And given, in inverse manner, let's provide some tensor, then we just calculate this gamma m, so it's the strength of the jets, then we can get the special flow by using this formula.
There's a question, 1 minute.
Yes.
Just a question, right? Because a Gaussian profile won't be periodic. Is that causing any issues?
Exactly. Yeah, it's a periodic continuation of the jets. Exactly. Yes. Thank you for the question. Yeah, it's a periodic extension of the jets. Yeah, as you can see, some chunks here.
But commensurate so that it doesn't fill up the whole thing, I guess. Right?
Yeah. So could you repeat it?
I said it's periodic, but in a way that is commensurate, so you don't get an infinity of images or something.
Right. Yeah. Yeah.
Is there a cutoff? That's all. Is there a cutoff function? Once it extends throughout all space, right?
Sorry, I couldn't hear you well. Sorry.
You have to sum all of those Gaussians, the ones from the images, from the periodic.
Yes, it's a periodic extension, but not. Yeah, they don't cover whole space.
I mean, that's because it's a very narrow Gaussian, so it's de facto.
Yeah.
zero.
Okay. So in mathematically.
Okay, there's a
so
mathematical.
jets should be compactly supported for the, but for the
Yeah, so he's
numerical
saying,
reason, yes.
Physicist will take your answer, a mathematician wants compact support.
Yeah,
Is that correct?
that should be compactly supported. But here, for the numerical reason, I have chosen the Gaussian profile.
Okay, fine, just understand.
Yeah, sure, no problem. It's fine. This is,
Now, of
yes.
course, we can use the Friedrichs modifier and things like that. But here I have used the Gaussian. Okay, so let me go back to yes. So the Buckmaster et al.'s construction. There are two things we can prescribe. So the one thing is the energy as a function of time, E of t, that can be prescribed. And there are other things. So there are other things. So it's a scaling exponent, h. So now I like to talk about how to prescribe exponent h with in their construction. So yeah, we have seen the Mikado flow, so-called Mikado flow. So the energy spectrum of this particular example looks like this. So it has some flat part and then it decays super exponentially. So in the mathematical construction, the perturbation takes roughly this kind of formula. And u sub q plus 1 is u sub q plus this perturbation. And we just continue this, yeah, we just replace these perturbations, then this velocity fields can be given by this way. So in fact, the constant before this Mikado flow is chosen in such way, yeah, it is chosen in this way. So this Km is the characteristic wave number at the nth iteration. So this W has this kind of energy spectrum. So this this summation can be interpreted in this way. So this purple curve is a W. So the next one is shifted by Km over 2 pi into the right. And then we have factor here. So factor K1 to the power minus h. So we shift a little bit and then go the shift to the downward. So if we repeat this shift to the right and shift to the downward and adding these energy spectrum of each Mikado flow, then as an envelope, we can have a nice spiral following k to the minus 2h minus 1. So that gives you the prescribed scaling exponent. So this is the way, roughly the way to impose the prescribed scaling exponent in their constructions. Okay, so since the paper is the rigorous mathematical proof, they have a lot nice estimates for the error and the velocity. This is basically the derivative of the velocity and the energy for the velocity, and there are some nice estimates for the energy of the q's velocity and so on. Okay, and formally the mathematical constructions is divided to 3 stages. The first one is modification and gluing and perturbations. These 2 parts, the 2 stages are explained in a heuristic manner. Okay, so the precise formula of the perturbation is a bit more complicated than I described before. In fact, the perturbation is given by the Mikado flow, but here, please notice that this argument is a Lagrangian label, not the Eulerian X. So this is a quite technical form, but we have used in the mathematical constructions and in the numerical simulation also. We let the Mikado flow evolves in by way of Lagrangian labels. So that itself is quite interesting things, but today I'm not going to talk about in detail. Okay, so now so this is in the remaining 5 minutes or so, I will show you some numerical results. Okay, so their solution at the Q's iteration has a characteristic wave number. So K sub Q is given by 2 pi times a to the b to the q. So this this caret is the seeding function. So here I have chosen the parameter a to a equals to 3 and b is 1.15 and alpha, which I didn't talk about today, but alpha is another important parameter in the construction. So is chosen here is 10 to the minus 1. So as a prescribed energy, I have chosen the linearly decreasing one. So some constant b and some constant a is specified. So this is the energy as a function of time. So this purple line is a prescribed energy. So it's there. Yeah, it looks flat, but actually it's a slowly decreasing, linearly decreasing function. And also the other ingredient which I prescribe is exponent. So as a body of the exponent, I have chosen 0.30. And as an initial velocity field, I have chosen 0 velocity field. So from 0 velocity field, according to the recipe of the Buckmaster et al., we can build a U1 and U2 and U3. So the energy of U1 looks something like this. So there are some oscillations, but here we have a straight line. So we constructed U1. So from U1, we will use the gluing and so on, then the perturbation and adding perturbation. We can have U2, and from U2, and we can have U3. So and U1 has some oscillations, and U2 is in this scale it looks like almost like a it looks like some straight line, but if we magnify it, it has some wiggles. And for the energy of the third iteration, we have some variations here. Okay, so the vorticity field. So this is the fundamental Mikado flow we talked about. So here I showed you the U1 constructed from the U0. The U0 is 0. So basically this U1 is the same as the Mikado flow, but this U1 is actually the 3-dimensional tiling of this fundamental Mikado flow. So U1 is the Mikado flow with some factor, K1 over 2 pi. The K1 in this case is 4. So the tiling, so by tiling, I mean, so this is fundamental Mikado flow, extends from 0 to 1. So it's a whole periodic domain. So we shrink this one to one quarter and put it here. And then we just tiling these tiny Mikado flow, then we can have U1. So, but for the U2, we are solving the classical Euler equation, and also the perturbation involves some inverse Lagrangian map. And because of those time development, now U2 start to have some convoluted or wiggled jets. So this is a snapshot. and some chosen time. And then we can just iterate the constructions. And now I showed you the U5. So U5 is qualitatively, it's very much the same as this U2. So actually this U5 is tiling of, it's a 10. This K5 is, K5 divided by 2 pi is 10. So you can see some kind of pattern in, for example, this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, and this part is split. But you can see some 10 layers in the U5. That's a reminiscent of the tiling of the Mikado flow. Okay, so the energy spectrum. So I showed you the energy spectrum from U2 to U5. So U5 is some bump here, and it doesn't look like having the power law scaling. So it's quite discouraging. And the grid points for this numerical simulations is 500 cubed. And if we like to go to the U6 and U7s, we need to increase the number of grid points. But anyway, so I stick to U5 up to fifth iteration here. So I calculated the second order longitudinal structure function. So U5, yeah, it's a snapshot, just a snapshot. I just take the spatial average for the second order longitudinal structure function. So U5 looks like this one. So it starts to have some kind of scaling, which is consistent to what we prescribe. So now I'm interested in having higher order fluctuations. So now I calculate the fourth order longitudinal structure functions. So for the U2, looks like this one, and U3 is green, and U4 is blue, and U5 is this one. So yes, so U5, yeah, let's just observe the scaling of the U5. So U5, if this flat part is a converged scaling law for the UQ, yeah, there are some probabilities. This scaling range keep changing as we increase the iteration number, but let's, for the sake of argument here, this part is a converged scaling law for this UQ. So this slope is close to 0.4, and that's quite different from what we prescribe here. But the problem of this value is this exponent for the fourth order longitudinal structure function is smaller than that of the second order structure function. So this implies unboundedness of the velocity, which is argued in the textbook of the Frisch. So that's a bit weird. And now I showed you the PDF, the probability distribution density function of the longitudinal velocity increment. So these three R's are within this range. So as you can see, yeah, this is a PDF of the normalized increment. So by normalization, I mean the mean of 0 and the standard deviation is 1. So the PDFs do not, they don't collapse each other. That indicates non-zero similarity for U5. So that means, if this is real, then those weak solutions are not so similar. So in some sense, so that weak solutions has a multi-scaling property. Okay, so this is basically the end of my talk. So I talked about the mathematical constructions of paper published 2019 by Buckmaster, Lellis, Szekelyhidi and Vicol, and I briefly described the mathematical constructions, and I implemented their constructions to the numerical simulations. But yeah, today I didn't discuss in detail, but there are several numerical cheating I have done. And given those cheatings, so my simulations, the result of my simulations may not be 100% faithful to the mathematical constructions, but now I showed you nevertheless the preliminary results of the numerical simulations. So the iterative construction of the numerical simulations reaches now 5, and it shows some quasi-regular structure, so that is as expected. And from the structure functions, yeah, it is, the simulation indicates some non-self-similar structure, and if this is true, then it is quite interesting to have a proof of the solutions of this construction is actually intermittent. So lastly, the word of warning is there are several numerical cheating, like the Mikados are not really compactly supported. The thickness is finite, and these cheatings may have some bad effects on these results. So yeah, we should be careful, but okay, so I stop here, and thank you for your attention.
Thank you very much for a very interesting talk. There is one question. So Bartosz, you want to ask your question first?
Yes, thank you very much. It's very, very interesting. So I was wondering if you prescribed a fixed energy profile and take sufficiently large value of the Hölder exponent h and consider sufficiently short time window, you could actually use this construction to build a classical solution to Euler.
So you mean prescribe the constant energy?
Yeah, constant energy, sufficiently large h, and the sufficiently small time window, so that you're within the local, you're within the interval of local existence. Mm-hmm. Would this construction give you a classical solution of Euler?
The classical solution to Euler. Okay, so in the mathematical sense, the constant energy cannot be prescribed, but the decrease of the energy can be arbitrarily smaller. Mm-hmm. So, but the exponent, the largest exponent, which one can prescribe within the mathematical construction, is 1/3 minus epsilon.
I see. Okay, so it is by construction a weak dissipative solution.
Right.
Okay, I see. Okay, very interesting. Thanks a lot.
Thank you. Yeah, you're welcome. Thank you for your question.
The solution cannot be smooth because this convergence is in L2. That's bar. Mm-hmm. So it cannot be classical solution.
Mm-hmm. Yeah, okay. Mm-hmm.
Okay.
Thank you.
There's a question from...
thanks for a beautiful, very interesting talk. I really enjoyed it. I was wondering, so I guess the H 0 point chosen to be close to 1/3. Is it? But there's a resolution constraint, right? Basically, as you shift these spectra down to the right, then resolution is eventually going to kill you. Do you think it's possible to play with this H a little? I mean, there's not a huge amount of room, I guess, but to be able to pick a different H to get something that can fit within the resolution constraints better to iterate the past 5?
So your question is the choice of H
Yeah, do you think
has
right, because it looked like with 512 cubed, you said you could only go up to q equals 5 before basically the structures got too small. But do you
yes.
play with the H so that you get a faster, a more rapid decay?
Yeah. Yes. Of course, the choice of H and the choice of other parameter like the wave number is given by this formula, and those choice of the parameter and the prescribed exponent H determines how far we can go with a given resolution. I mean, how many iterations we can go with given resolutions. And if H is very small, then yeah, there are some other technical things, but yes, and as you guessed, the finite, yeah, okay, so the resolution we need to calculate the resolution strongly depends on the choice of H and the choice of A and B and alpha. Am I answering your question?
Yeah, thanks. Also, just out of curiosity, did you happen to, you didn't show us, but did you happen to push it to higher iterations just for fun to see what it looked like? Even though you can't maybe trust the resolution?
Okay, so the trusted resolution, yeah, for the U2 and U3, I have calculated the same thing with different resolutions, and yeah, actually the constraint on the resolution is quite a big problem, and yeah, that's need to be checked in a yeah, it's a very good question.
Thank you.
Yeah.
Jeremy has a question.
Hi, Takeshi. So,
Hi.
very nice talk. Thank you. So I had the connected questions because this is basically the numerical barrier. I mean, it's double exponential. So could you think about different procedures? So, for instance, during the gluing or during the estimation of the error, that would increase this convergence. I mean, that will make the convergence faster. So so it seems to me that, for instance, the gluing procedure is just some piecewise linear approximation. So that if you go to higher order approximation, I think it will improve the procedure. I mean, the convergence.
Mm-hmm. Okay, so yeah, that can be done in, for example, in the you mean in the framework of theoretical physics, not to have the rigorous mathematical proof.
Yes, or as an engineer also maybe.
Yeah. I guess so. Yes. Yeah, there are. Yeah, I've never tried, but yeah, there's a hope to have nice theoretical arguments or theoretical way to boost this procedure to have interesting solutions.
Oscar has a question too.
Takeshi, I have a question. So with your choice of A and B, the range is like 9, 2 pi times 9 from the wave number. So
yes.
Is it big enough number to see effects?
Yes.
Right.
And
yeah,
I'm repeating what Jeremy said. I think that they use their procedure for mathematical proof, but you are not concerned with mathematical proof, so you can probably do it better doing your own way.
Yes.
That scheme.
Yes.
Following that scheme.
Right. Yeah. But actually in the mathematical construction, the parameter A should be much larger than 1. So it should be 10, 100. but that cannot be implemented numerically.
Sure.
So I like to, yeah, I'm very like to know how, yeah, how much is enough, how small, yeah, I don't think 3 is a good choice. It should be larger.
Okay, if not, we should thank
I
Takeshi.
have a question, sorry.
Yes.
It raises a question. Hold on.
Yeah, sorry. I just want to make a comment and a question. If you
Yes.
go into the gluing part, when you introduce instead of the Eulerian x by the Lagrangian A of x and t,
Okay.
the A of x and t.
Gluing and
When you do the Lagrangian A of x and t.
okay, so the perturbation.
Yes.
Yeah.
Yeah, I just want to make a comment here that this particular step is really one of the main contributions of Isett, because, you know, I mean, you laid out the program of Buckmaster, Vicol, and Szekelyhidi, but this was one of the main issues in the contribution of Isett, which is, I just want to give the full picture, because this was a major step in order to reduce and to make, because at the beginning they were marching from exponents like less than 1/10, blah blah blah, until they get to the 1/3, and there was like incremental steps, but each step was really quantum jump in some sense. So this is a remark. My question is, there are two parts. The first part, in your numerics, in the computations, when you do the gluing step, you go forward and backwards, and you're trying to integrate Euler equation. Now I mean, many people says, well, no matter how good you are, you have to put some viscosity. So do you have any viscosity in your numerics when you go forward and backwards, and then the glue, therefore, do I see traces of this viscosity in this thing or not?
Okay, so I'm using the spectral method. So yeah, to solve the classical Euler equation. And the numerical viscosity is not big if I compare the numerical method to the other numerical method. And since I'm solving the Euler equation in backward and forward, and the time reversibility is satisfied something like a 10-digit accuracy for these simulations. Am I answering your question?
Yeah, to some extent. So there is some viscosity. I'm just basically maybe concerned if one would like to push this further. I mean, are we doing not Navier-Stokes, but localized version of like local viscosity Navier-Stokes versus Euler? I mean, just from the numerical point of view, and therefore, are we at the situation where we are, in fact, doing the non-uniqueness part of a la Buckmaster and Vicol, like the Navier? I'm just basically making comment that just to be careful about that. And the second question is, and this is basically to distinguish, your U0 of xt is not the initial value, it is the initial iterate step. But can you make comments about what happens when we talk about the limit of these UQs, because Q goes to infinity, we converge weakly, etc. Do you have anything about which initial value we are solving? Are we at all talking about an initial value, or just, of course, the purpose is to construct a solution?
Yeah, correct.
But can we, I mean, you specified the E of t. Can one specify initial value in addition, and what happens in that case?
Yeah, okay, so yeah, this is not the solution to the initial value problem. So yeah, if we start with a zero velocity field as a U0, then the solution for the time zero is always some Mikado flow, the straight Mikado flow. So in that sense, the solution is just one solution, and it has nothing to do with initial value problem.
Okay, Well,
Yeah.
I mean, thank you very much for a fantastic talk. Really, really, thank you very, very much. I enjoyed it very much. Thank you.
Yeah, thank you for your word. Yeah, thank you.
Thank you, Takeshi. Let's thank Takeshi and all.
Thank you so much.